And so those three solutions could be. So one potential solution is this. Give user a structure named node. So they can create those little nodes, right? They can create them. Something like that. They can create them. And give the user options like functions. Functions to link them. So there could be a function to add to link nodes together or to unlink them. And so separate functions right here could be used to arrange and create the actual sequence, right? So have only a structure, and a structure just like this. A structure like the very simple primitive structure with no member variables, and have a bunch of functions, free functions, that we can pass these nodes to and say, okay, let's link them. Let's point one to another, or insert or remove things from the list. So this is one approach. The second approach, this would be a C-style, right? A C-style approach. The second approach, restart the clock. Another approach is this. How about we create yet another object, which will be serving as a container for those things, right? So kind of wrap this all around and have this container, allow to all of these, functions which would allow to manipulate nodes internally become part of the implementation, become member functions of this container that implements list. And guess what? The node class is then completely hidden from the user. All that the user is doing then is just create the list object and call functions to say create new node, insert new node, remove, and so forth and so forth. So that the nodes and the actual list internally is maintained internally, entirely. So the user does not manipulate the individual nodes, only manipulates the container that wraps it internally. And yet the third approach, so this would be actually a C++ standard library approach. The C++ standard library contains list container. You can create a list and start using it without even thinking about the actual internal manipulation of individual nodes, and the fact that there are some really interesting links that are taking place internally. And the third solution would be to actually create the node object, and each individual node object will have its own interface to add, remove, and so forth. Add, remove, link elements in the list. And then simply by instantiating these objects, we can call member functions on each one of these member functions on these nodes, and basically tell this node to link with this node, and then tell this node to go ahead and link with this node, right? And then later on to say, okay, we just created a brand new one right here, and so we actually want to insert it. We want to insert it before this node. This way, what this insertion should do is essentially repoint this, right? So get rid of this link. Instead say, oh no, the new arrangement is going to be that this one should be pointing here, and this one should now be pointing to this one, right? So we just, instead of linking this one directly with this one, we just inserted a brand new element. But maintain the whole thing at the node level. So the user has to know, should have enough knowledge that they need to instantiate those nodes and then call member functions specifying different instances to be able to link them. So this is the third potential approach to implementing a list. And this is, by the way we're going to be exploring it, and the way we're going to be using it in our next homework. And then, of course, we'll see examples of the C++ standard library using a list from the standard library. So we're going to cover all of these aspects. Okay, so this is what this particular slide refer to. A C-style approach is using global functions and structures that represents data, some payload and pointer to potentially to another node. The C++ node class approach is the third one that we discussed. So we have some private member variables inside the node class and public member functions on that node class, or that we're going to design ourselves, right? We'll be allowing manipulating the list operations. Link, unlink, insert, remove, and so forth. And finally, the standard library approach is that it maintains the double link list and it maintains it internally. You only tell it to insert a new element, to locate a particular element, to remove that element, and so forth. You're manipulating that container approach to your node list. So it's completely managed for you. You just say what you want to do with internally stored elements, and the container will manage it all. Or the nodes themselves can be manipulated, and that's the alternative approach. So here's an example, and this is where again it gets a little bit tedious, but one quick observation here. It wouldn't be possible to work and even think about a linked data structure that uses uniform nodes and provides them an ability to link to one another, to point to one another, without a pointer, right? So pointer is an absolute crucial design element or building block, a little brick that makes it all possible. If we were not able to express pointer, then we would just as well forget this and maybe ask our programming language to provide us some high-level facility that implements something like this, some sort of collection that would be named list, and we just manipulate it somehow. But there is no direct way of manipulating it at that level. So in C and C++, of course, the manipulation of individual nodes becomes possible simply because we have pointers, and pointers are variables. And because pointers are variables, we can tweak them any way we want. So let's explore this. Structure node. Remember, we're discussing the C style, the most primitive potential approach to this. C style solution. So structure node exists, right? So node has integer data. That's something useful that each node stores. Of course, there could be the whole array of integers here, or other things, strings and text and blocks of memory, whatever. There could be a lot of things that we could store in a node. But this is just for demonstration purposes. We just have a single integer there. And this is, of course, the link to the next node. Okay. So we say, let's design a function that says insert in front. Insert in front. So the idea is this. Here's some nodes. So here's node A. It's currently pointing to node C. We want to, so somehow we achieve this structure that we have node A and node C, and node 8 is pointing to the node C. Okay. Then we want to insert something in front of A. And of course, the result should be that A points to B, but the chain link to C is not lost. So that the outcome of insert in front is that if there was another node already present, then we should not lose the link to it. So A is now pointing to B, and B is pointing to C, and C does whatever it wants in its own turn. So, so the interface to this function is such that we say first parameter to this function is the node, and I assume it's this A right here, node A. And then there is a brand new node, which is node B, new node. And what this function does, insert front, it says new node right here. By the way, I can say copy image, right? And then I could go right here and paste it in, I guess. So we can talk about it, right? So let's actually save this segment.